So I think we can start now the afternoon session. The first speaker of this afternoon is Andrea Pelissetto, who will tell us about the three-dimensional U1 scalar gauge theory. And please.
Yes.
Yes.
Okay, so we can use this one.
Let's see, can you hear me now? Yes, okay,
Yes.
okay. You see, a theoretical physicist. So we solved the problem very easily. Okay. So my main interest, the main interest in this kind of systems now is in the context of emergent gauge theories. Emergent gauge theories is a new paradigm in condensed matter physics in quantum to explain the behavior in 2D quantum transitions. And it's the description of systems in which there is no microscopic gauge symmetry. So you have a system in which there is no gauge symmetry at the beginning, at the microscopic level. But the gauge symmetry comes out in the effective description of the model at the transition. In this sense, it is an emergent gauge symmetry because it does not belong to the microscopic model. And the typical example in this business is the spin 1/2 antiferromagnet on a square lattice, or in general on bipartite lattices. And here is one of the paradigmatic examples. So we have the system. In the systems, we have a couple of Heisenberg spins, quantum Heisenberg spins, spin 1/2, that interact in this way with couplings that depend on the bond. So imagine we have two types of bonds, thick bonds and dash bonds. And of course, if the coupling on those bonds is the same, we get just the standard antiferromagnetic Heisenberg model. And we know what is the order parameter is just the staggered magnetization. It's true in the classical case, but it's also true in the magnetic case. Essentially, spins on neighboring lattice sites are just directed in the opposite way. And we know what are the excitations. There are gapless excitations, which are spin waves. So, and if the J's are identical on all bonds, we know exactly what is the ground state of this Hamiltonian. But then, let's go back here. Let's imagine that we put 0 on the coupling, we put J equal to 0 on the dashed lines. In this way, we have just pairs of interacting spins, and they are completely decoupled from the others. And of course, when you try to find a ground state, okay, it's just a two spin problem, and the ground state is formed by a spin 0 singlets. So each pair of spins on a thick bond pair in such a way that the total spin of the pairs is exactly 0. And of course, by varying the coupling on the dashed lines, you can change the type of behavior, and there is a quantum critical transition in between. So the main problem, and this has been a problem for the last 20 years, is just to understand and describe this transition between this Néel state, antiferromagnetic state, and what is called the valence bond solid state, which is the other one in which you have singlets. And of course, it's very difficult to have a description, an effective description in terms of standard order parameters, because here we only have the spin S. So the idea, which is below these models, is that of introducing fractionalized order parameters. So the idea here is to replace the spin S, which is a vector, if you think of rotation, with a spinner, the complex spinner Z. And the relation between S, then the relation between S and Z is given there. It's just Z bar Pauli matrices times Z. And of course, you see immediately that the relation between Z and S is not unique. You can, of course, change the quantity Z by a phase and nothing changes. So there is a gauge invariance in this case. So the definition of Z is defined modulo gauge transformations on the field Z. What is the advantage of this description? The advantage of this description is that if you use Z and not S, you have an order parameter, you have a theory which describes both phases, the antiferromagnetic phase and the VSB phase, the phase in which you have the singlets. So in this way, we have transformed the original model, in which there was only a spin, S, into a new model in which the basic field is a complex spinner, but with gauge invariance. This is what I mean by emerging gauge invariance. There is no gauge invariance at the beginning, but now in my descriptions in terms of Z, there is gauge invariance. And then, of course, you just write down a Hamiltonian for this field Z, and you get the abelian Higgs model. So this is the way in which this gauge invariant theories come out in many condensed matter problems. So there is no gauge invariance at the beginning, but the gauge invariance comes out when you describe the interactions in terms of a new field, which typically is fractionalized. Fractionalized because we start from a spin which is a vector, spin equal 1, if you like, in terms of O3 rotations, and you replace it with something which is spin 1/2, the spinner Z. So this is what I mean. So this is the reason why we want to study this kind of model and why these models have been so studied in the last years. So now let's go back to standard classical statistical mechanics, standard classical field theory. What is the abelian Higgs model on a lattice? So on a lattice is defined in this way. We have a field, a unit length scalar field Z, which has NF components. And we want to have an interaction which is gauge invariant. So we add a real U1 field, AX nu, defined on all lattice bonds. The interaction between the fields Z is standard, completely standard. So it's just a nearest neighbor coupling in which we add the gauge field lambda, which is the exponential of A. But then we have to introduce also an action for the gauge fields. And for an abelian gauge field, there are two possibilities, which I will discuss. The first possibility is to use a gauge compact action, which is the standard Wilson action, which means that we just take the product of the lambda fields, or if you like, in the standard notation of QCD, of the U fields along the plaquettes. And this is the standard compact Wilson action. But for a abelian theory, you can just discretize the standard Hamiltonian, the standard action F square. And then you get something which is written there in the last line, in which you write your interactions in terms of A and not in terms of lambda. It is possible to have both theories. They have a different behavior, the different critical behavior. And if one looks carefully at the derivation of the confined the derivation of the effective model for the confined criticality for the antiferromagnet, you realize that the correct Hamiltonian, the correct action that describes the theory is the non-compact one. The non-compact one that is related to the fact that when you do the path integral formulation of the antiferromagnet, there are topological phases, the so-called Berry phases, and these Berry phases kill in some sense the periodicity or some of the periodicity of the interaction, and then you have something which is naturally non-compact, not really non-compact, but mostly non-compact. So I will discuss the behavior of these two models independently. So let's first see how one predicts the behavior in this case. So there are essentially two approaches to obtain the critical, or at least to predict the critical behavior of a gauge theory in 3 dimensions. The simplest one is the so-called Landau-Ginsburg-Wilson approach. In the Landau-Ginsburg-Wilson approach is the approach that we use, for instance, to describe standard ferromagnetic systems. We just identify the order parameter just on the basis of symmetries and global invariance of the model. And then we write a field theory for the order parameter alone. Here, one works exactly in the same way. Of course, here we have a system which has a gauge invariance. So we choose an order parameter which is gauge invariant, of course. And then we write a field theory for the gauge invariant order parameter. In this field theory, there is no gauge field. There are no gauge fields at all. So we have just a standard field theory, a standard lambda phi 4 theory for the order parameter of the model. And in this framework, the only role that is played by the gauge fields is that of selecting what is the correct order parameter, because the order parameter should be gauge invariant. So gauge fields are important in the sense that they select which order parameter is the correct one. But apart from that, they have really no role. And the transition is essentially controlled by two things: the global symmetry of the system, not the local symmetry group, but the global symmetry group, and the representation of this order parameter. It means how this order parameter transforms under the global transformations of the model. And in this sense, the gauge symmetry group is essentially irrelevant in order to define the behavior of the system. And this is the approach. This is never stated clearly in the original paper by Pisarski and Wilczek, but this is essentially the approach taken by Pisarski and Wilczek to predict the behavior of the finite temperature transition in QCD. They just define an order parameter for the transition, look at the global symmetry group, which depends on the flavor left and right symmetry, then they write down an action for this order parameter and look at the fixed points in 3 dimensions for this model. This is the approach that they take, but implicitly they are just assuming that gauge fields play no role except in defining what the order parameter is. So this is the basic assumption of this approach. Of course, you can take a completely different approach, because beside the lattice model, there is also an abelian Higgs field theory. And you may think, okay, but this is not correct. The previous approach is not correct. What I should do is just study the abelian Higgs field theory, look in the standard Wilson-Fisher approach at the fixed points which are present in this field theory, and those fixed points will control the critical behavior. In this case, if the fixed points correspond to some non-negative, non-vanishing value of the gauge coupling, of course, that fixed point is not a fixed point which can be obtained in the previous approach. So we have two completely different approaches. On one side, we have an approach in which gauge fields are eliminated from the beginning, and we just use the standard field theory for the order parameter, for the gauge invariant order parameter. And then we have a second possibility. The second possibility takes the gauge field theory, which is associated with the model, seriously. So we look at that field theory, try to investigate which are the fixed points which are present in this field theory. And if there are stable fixed points under the usual resonalization group flow, then those fixed points are those that control the critical behavior. And I will call these fixed points the charge fixed points of the theory. So what is happening in the abelian Higgs, in the lattice abelian Higgs model, and in general in non-abelian lattice gauge field theories in 3 dimensions? So we have done a lot of studies. We have studied several models, and essentially we have found the charge fixed points. I think we have found charge fixed points, but only when the number of flavors, the number of components of the scalar field is sufficiently large. So for the abelian Higgs model, there is good evidence. I will try to convince you that there is a charge fixed point that controls the critical behavior when the number of flavors is at least larger than 10. In non-abelian systems, it's much more difficult to find charge fixed points, but we have a candidate in this theory, in a theory with SUN global symmetry and SU2 gauge local invariance, but you need at least 40 flavors. In the system with 20 flavors, we investigated a system with 20 flavors, there is no evidence for a charge fixed points. So charge fixed points appear in this kind of models, but they appear when the number of flavors is sufficiently large. And if it's really true for all models, this means that they are not really relevant for physical problems. Because of course, in physics, we need, I mean, in the previous example, the number of flavors was 2. So it's not clearly the case here. So let's try to describe what comes out of simulations. So we have investigated several models. First, the Compat and abelian Higgs model. This is something very old. This has been studied several times. And we have investigated for a different number of components. So let's remind you that this is the model in which we use the standard Wilson action for the gauge coupling. And the behavior is written here. The phase diagram is there. So there is a single transition line that separates two phases, a phase which is small j, which is strong coupling phase in which the scalar fields are disordered. And then there is another phase, large j, in which the scalar fields are ordered. So we have standard order-disordered transition, which is completely independent of kappa, of the coupling of the gauge fields, of the plaquette action. Whatever value of kappa you use, you always obtain the same type of transition. The transition is always of the same type. Of course, as I told you, I have to choose a gauge invariant order parameter. For n equal to is exactly the Néel order parameter that I was using, that I was mentioning in the previous case, so z bar z z. And for generic n, the natural combination is the adjoint combination of a z bar and z. So z bar a zb minus the trace. Go back here. Okay, so let's see what are the predictions of the Landau-Ginsburg-Wilson approach. Well, the predictions are very simple. As I told you, in the Landau-Ginsburg-Wilson approach, one identifies the order parameter. So the order parameter, we said, is a Hermitian traceless scalar combination, z bar z minus the trace divided by n. And this is when you constrain this quantity, you see that the order parameter is nothing but a matrix which transforms in the adjoint representation of the global symmetry group. And then in order to predict the critical behavior, we write down the 5-4 theory for this order parameter. And what is well known is that whenever you have a matrix order parameter, the transition is typically of first order, simply because you always have this trace of 5 cubed term. And whenever you have a 5 cubed term in your Hamiltonian in 4 dimensions, then you always have, it's easy to show it using mean field arguments, you always have a first order transition. So in this case, we predict a first order transition, except in one case, when the number of flavors is 2, because for 2, there is a simplification, the proof is written there. Since we use an order parameter which is traceless, so the trace of phi is equal to 0, for a 2-dimensional matrix, it's trivial to show that also the trace of phi cube is 0. So when the number of flavors is equal to 2, the 5 cube term is not present. And then it's very easy to show that also there is a relation between the trace of phi squared, the trace to the 5 to the 4th. We just have 2 eigenvalues again. And we end up with the standard theory for a 3-dimensional vector. And so we can predict the transition to belong to the O3 vector universality class. So it just behaves as a standard Heisenberg model. So these are the prediction. And then we did the numerical simulations, and everything comes out exactly as it was predicted. Because for nf equal 2, we get exactly O3 behavior. For any value of kappa, we simulated the model for several values of kappa equals 0, and kappa non-vanishing, and we always obtain clear evidence of O3 behavior exactly as predicted. And for nf larger than 3, we get a first order transition. The nice thing here is that the latent heat, this is what somewhat unexpected, I must say, the latent heat and the surface tension both increase with the number of flavors. So the transition becomes stronger, the first order nature of the transition becomes stronger as the number of flavors increases. So this means that we always have a first order transition, including the case in which the number of flavors goes to infinity. And in a sense, this contradicts something that, okay, it was assumed in the last 40 years, the early works of Pettorino, Di Vecchia, and several other people. They studied the large N expansion in the CPN model, which is the same model, but for kappa equals 0, but we said kappa is irrelevant in this framework. So they studied this model and they just made a 1/n expansion. They were predicting nice second order transition. They had predictions for the critical exponents. Nothing of that is correct. It's not correct because, of course, when you do these calculations in this 1/n calculation, of course, there are lots of technical assumptions that you make. And the fact that there is no agreement between calculations, the analytic calculations, and the numerical simulation simply means that one of those technical assumptions fails. So we try to understand which of this technical assumption fails, and we realize that there is one crucial quantity, one crucial assumption in these calculations. Typically, one assumes that at the saddle point for nf going to infinity, the gauge field, here I call them u, but it was the previous lambda, is equal to 1 modulo gauge transformations. And we did simulations up to 100, up to number of flavors equal to 100, just to see if that assumption was correct. And we saw that this is certainly true for the order phase. So in the upper part of the phase diagram. So in that region, if you look at the behavior deep in that phase, you see that the gauge fields order when you increase NF. So as long as you increase NF, you keep increasing NF, and you see that the fluctuations of the plaquette decrease strongly. But in the disorder phase, this doesn't happen. You increase NF and nothing happens. The plaquette is always disordered. So in the limit, NF going to infinity, there is no ordering. So our assumption that U is equal to 1 for NF going to infinity is not correct. And this is the reason why those calculations fail. Okay, so now we know that in the standard compact abelian Higgs model, nothing happens. Everything is well described by the Landau Ginsburg-Wilson approach. There is no evidence of charge fixed points. Charge fixed points are not present in the compact abelian Higgs model. So let's turn to the non-compact version. The non-compact version is the one in which the gauge action is expressed in terms of the field, not in terms of the use. And remember that the scalar matter interaction is always in terms of use, but not the gauge action. The phase diagram is this one. And if you remember the previous phase diagram, there is an additional line, which is called here MH. I don't want to explain why it's called MH, but note that there is a new line which separates two different phases in the region in which the scalar fields are ordered. So we have a new line where the scalar fields are ordered. And so we have two different, what is called molecular and Higgs phase. So let's try to understand why there is this additional line, studying the limit in which J goes to infinity. So we push the matter coupling to infinity, and want to understand why there is that transition, which is called O2 transition, just at the top of the phase diagram. So what is happening for J equal to infinity? Okay, you look at the action. So essentially for J equal to infinity, we want to maximize the action. We have a ferromagnetic system, so we can do that locally. So we maximize the action on each single bond. And when you maximize the action on each single bond, simply means that ZU should be 1. That's the maximum value it can take, because remember that Z has modulus 1. So this implies that relation that between Zx and Zy on two neighboring points. And then you can generalize that relation considering paths which go from any pairs of size X and Y. And here is just an example of what is happening. If you take X neighbors of Z, which is a neighbor of Y, and you see the product of the links, of the gauge links on a path which goes from point X to Y. Of course, this relation can be generalized to any pairs X and Y, and in particular, you can just take a loop which starts an X and goes back an X going through a plaquette. You get that relation that Z of X is equal to the plaquette times Z of X, but Z of X is phase, cannot be 0. So that implies that the plaquette is equal to 1. Pi of X is the plaquette is the product of the links around the plaquette. So this means that the plaquette is 1, which means that U is 1 modulo gauge transformations, which implies that A is a multiple of an integer. So A is 2 pi n. n is an integer which belongs to Z. So for j equal infinity, A is no longer a real field as it was at the beginning, but it's a discrete field which takes values on integer multiples of 2 pi. And the new theory is again a gauge theory, but now the gauge group is no longer R, the additive group of real numbers, but just Z, which is the ratio of R divided by U1. Is the quotient group of of the real numbers by U1. And this model is very well known because using duality, you can prove that this model has an XY02 transition, standard transition in the XY02 universality class. Okay, I'm fine. So this is now the situation at large j, at j equal infinity. So we have a small k region in which the fields are disordered and this n fluctuates wildly. And then we have a large k region in which gauge fields are ordered, and essentially n is on most sides equal to 0. So we have this different behavior. So so now we understand what is happening in these two phases. And now it's clear that the molecular phase, or the phase which corresponds to small k, is essentially the phase which occurs in the compact model. Because in the compact model, A is periodic. There is no limitation on A. And so it corresponds to the case in which n can fluctuate wildly. If it can move easily from any value to any value, it's just like having a periodic gauge field. So the molecular phase, the small k phase, is the phase corresponds to the phase, to the only order phase that appears in the compact model. But the new phase, which occurs for large k, for large kappa, that phase is not present in the compact model, but is a peculiar phase which only occur in the non-compact version of the abelian Higgs model. And so this is the phase in which we want to study, because this is the phase in which something new may happen. And indeed, this is the phase in which people were looking at the fixed points relevant for this deconfined quantum criticality. So we have studied the lines, the CH line. So the CH line, I just remind you, is the line which is between the ordered phase and the disordered phase for large kappa. So for small, the CM line corresponds to small kappa, the CH line to large kappa. CM, my assumption is nothing changes with respect to the compact case, because the molecular phase is identical to the phase, to the order phase of the compact model. The new phase is the so-called Higgs phase. So if something new should happen, that should occur along the CH line. And indeed, this is what is happening. We analyze the CM line, and for two flavors, we get O3 behavior. For a larger number of flavors, we always get first order transitions, nothing really new. Everything is exactly the same as it was in the compact model. Then we analyze the CH line, and here, for small number of flavors, we only observe first order transitions. This is the case for 2 and 4 flavors. But we found continuous transitions for 10, 15, 25 flavors. And of course, these transitions cannot be described inside the Landau Ginsburg-Wilson approach, because in the Landau Ginsburg-Wilson approach, there is no fixed point for those values of NF. So the natural scenario is that for these values of NF, we are really seeing a charge fixed point. So a fixed point which does not occur in the theory in which gauge fields are not present, but is a fixed point which occurs instead in the field theory, which is associated with the abelian Higgs model. So we looked at the results for the abelian Higgs field theory in epsilon expansion. And in this case, one finds that a charge fixed point really exists when the number of flavors is sufficiently large. And it's a little bit not very predictive, the expansion that you get here. As you can see, in 4 dimensions, it occurs when the number of flavors is larger than 183, with corrections which are huge. The first correction, when you put epsilon equal to 1, is larger than 1. So you see it's not very much predictive, but this essentially tells you that there is a charge fixed point for large values of NF, but we don't know exactly where it is. So it is possible that our values, our transitions for 10, 15, 25, which are significantly smaller than 123, are indeed described by the field theory. This is just a plot for advertisement, just to see the quality of the results that we have, just to be sure that we really have a continuous transition, and how we estimate the critical exponents. So this is a plot. On one side, this is the C over L, so the correlation length divided by the size of the lattice, expressed in the standard finite size scaling variable, which is J minus the critical value multiplied by the size of the lattice to the power 1 over nu. And if you do fits of this form, you are able to estimate the exponent nu. And then the other plot is the same plot for the susceptibility, for the magnetic susceptibility, as a function of the correlation length divided by the lattice size, which allows you to derive the value of the eta exponent, so of the field anomalous dimension, if you like. So these are the two values that we get for 25. We repeated the same analysis for 10 and for 15. And how can we be sure that we are really seeing the charge fixed point? Of course, epsilon expansion does not provide you any information, but fortunately there are calculations in field theory in 3 dimensions, directly in 3 dimensions, in the 1 over n expansion that predict what nu and eta are in 3 dimensions. So we have this expression to order 1 over n. So we compare the result that we are obtaining with the large n expressions. So here you see nu is the Monte Carlo estimate. Nu with sub ln is the large n prediction, and eta q is the Monte Carlo, and eta q ln sub ln is instead the large n prediction. And you see that for NF equal 25, numbers are essentially the same. Nu agrees within error bars, and eta differs by twice the error bar. So of course there are 1 over n square corrections, so it's already very nice that we have such a good agreement. Of course, if you decrease NF, discrepancies increase, as you should expect. But what is nice is that if you introduce a 1 over n square corrections and you fit its coefficient naively, then you can explain all these results. Of course, not such a big fit because we have 1 parameter and 3 points, but essentially you use 15 to fix the 1 over n square, and then you see that the NF equal 10 comes out more or less correctly. So this means that, I mean, I think that this proves in some way, or at least gives a very strong evidence, that these transitions are indeed charge transitions that cannot be explained by the standard Landau Ginsburg-Wilson approach. So they cannot be explained, and this is something that you should remember, by the approach which has been used by Pisarski and Wilczek, by the way. Of course, from the physical point of view, it tells you that the charge fixed point is not relevant for the physical case, because the physical case corresponds to 2 flavors, and there is no charge fixed point for 2 flavors. Okay, now let's finally discuss another variant of this model, which is the charge Q compact model. The nice property of this model, which is different from both the compact and the non-compact model, is that this model allows you to interpolate between the compact and the non-compact model. So let's see how it is defined. Definition is on top. So the model is compact, so the gauge action is just the standard Wilson action. So we just take the product of the U's around the plaquette. But the matter field now carry charge Q, which means that when I make it gauge invariant, I multiply U, which is the usual thing, by a factor of Q. Q is, of course, is an integer, which means that this is a charge Q system. In a way, if you think it is just changing the representation, the U1 representation of the matter, instead of having the fundamental representation, I'm using a higher order representation. with respect to U1 transformations. Okay, now let's see why this model interpolates between compact and non-compact model. So let's rewrite the model in this way. So reparameterize U in this way, like the exponential of IA divided by the charge, and define V as the exponential of IA. Of course, if I do that, A now varies between minus pi Q up to pi Q. So it's not a quantity which varies between minus pi and pi, but it varies between minus pi multiplied by the charge up to pi multiplied by the charge. And the action takes this form here. And as you can see here, the matter field part now is standard because V is the exponential of EIA. So there is nothing fancy there. But the gauge part now is written in this way, which is the cosine. And then I do just the usual, I combine the exponential and I use the definition of U. And inside the cosine, we have 1 over Q times the usual F squared, the discretized F squared, which is the way in which you prove that, of course, the Wilson action has the trivial continuum limit. If 1 over Q were A, and then you do the expansion, you just prove that this action has the correct continuum limit. But now, as you can see, if I take Q going to infinity, what is happening? Two things are happening. First thing, A becomes unbounded. So A goes from minus infinity to plus infinity. So now we have a non-compact gauge field. And second, 1 over Q in the cosine becomes 0, becomes very small. I can expand the cosine, and then I get, of course, 1, which I don't care, times the standard action for the non-compact abelian Higgs model. So this model interpolates between the two, between the compact and the non-compact non-compact theory. Why is this model interesting? Because this model on one side is compact, but it has a phase diagram which is analogous to the phase diagram of the non-compact theory. And now, again, how can we realize that? Is that for J going to infinity, again, we are taking this limit in which the scalar fields are completely ordered. We obtain again a discrete gauge theory. Because if you send J to infinity, the same arguments that we used before allow you to prove that V goes to 1, modulo gauge transformations. And if V goes to 1, looking at the definition of V, just tells you that A, again, is 2 pi times an integer. The main difference is that now A does not go from minus infinity to plus infinity, but only from minus pi Q up to pi Q, and there is periodicity, which means now that N is defined in the additive group of ZQ, which is the additive group of integers modulo the charge. And of course, when Q goes to infinity, you recover the old model because ZQ, of course, converges to Z. So this is exactly what you expect. So this is the phase diagram that we have when we consider the charge Q model. And in this case, you see, we have something very similar. We have one line that separates the disordered phase from the two ordered phases. And then we have two different types of ordered phases. And if you look carefully at the two ordered phases, you realize that there is small kappa region, which is analogous to the charge 1 phase, which are the only one that occurs in the standard compact model. But then there is also another phase, which I call the order and deconfine phase. And this phase is analogous to the phase which occurs in the non-compact model. So the problem is, okay, here we don't have non-compact fields, we have compact fields, but the question is, do we still have a transition which is controlled by the charge fixed point? So we analyzed this problem in detail, and indeed this is what we found. And this is a picture of a plot which expresses the Binder parameter in terms of the correlation length divided by L. In a certain sense, this is just like the step scaling function which is used by Lucia, just different choice of the variables, but the idea is the same. And exactly as in Lucia's approach, I mean, two models belong to the same universality class if they have the same scaling function. And indeed they do, because here you see I report data for charge 2 model, which in a sense is the one which is farthest away from the non-compact model, because we said compact model is recovered for Q going to infinity, while here Q is equal to 2. So it's really the worst case. So we compare the data for the worst case, Q equal 2, with the non-compact data, and they just fall exactly on the same curve. This is for N25, but we verified also for 15. So you see, it's not important to have non-compact fields to obtain charge fixed points. And this is relevant in the condensed matter community because non-compact fields means completely eliminate the so-called monopoles, while in this model here, you have some of them because you have still some kind of periodicity. But some are eliminated, not all. But it's just enough, this small change in the theory to obtain the charge fixed point, which is instead absent in the compact case. So conclusions. No, first, this one. So what we have done, we have studied 3 different models: the compact abelian Higgs model, the non-compact abelian Higgs model, and then we have considered this model, the charge Q abelian Higgs model, which interpolates between these 2 models. So what we find is that in the case 1, compact theory, we get just trivial behavior, O3 behavior for 2 flavors, first order transitions in all other cases. And for an F equal 2, for 2 flavors, all these models only have these O3 transitions. So for 2 flavors, there are no charge fixed points, and the description is just, I mean, it's completely performed if you use the standard Landau Ginsburg-Wilson model. Gauge fields are completely irrelevant. And we also tried to do some additional checks that the gauge field does not matter, because we have, this is ongoing work that we are finishing. We started the same abelian Higgs model, replacing the U1 group with a subgroup, the ZP subgroup. And if you do that, nothing changes again. As long as P is larger than 3, Z2 is something that's a little bit different because it goes over to the RP model, which has a first order transition. But as long as P is equal to 3, which is not much, the system behaves exactly as the U1 model. So you have a continuous global continuous gauge group, and you replace with just a group with 3 elements, and nothing changes. You always have O3 behavior. And this is due to the fact that if you have ZP behavior, the order parameter is exactly the same. You do not introduce, you're not able to introduce a different order parameter. The order parameter is exactly the same. And once you identify the order parameter, then the field theory is the same. It doesn't care about the original gauge group. So this is another check that the original gauge group is not relevant. We have been able to observe the critical fixed point, the charge fixed point in the non-compact case and in the charge Q case. But however, this requires a number of flavors sufficiently large. We don't know exactly what is the minimum number of flavors which are needed. We know that for 10 flavors, there is a charge fixed point. For 4 flavors, there is a first order transition. So it should be a number in between 5 and 9. Which number is, we don't know, but it's there. And of course, this means that this number is not relevant for the physics. One thing that comes out also of these calculations is that the epsilon expansion is not predictive. So imagine that when you do standard 1 loop calculation, so it means that you get the result in 4 dimensions, you get n star f, so the minimum value which is needed to observe a charge fixed point, which is 183. While in 3 dimensions, the real number is something between 5 and 9. So there is a huge difference between the numbers that you get from the epsilon expansion and the number that you get in 3 dimensions. So it's not predictive. So the only thing that you can get out of the epsilon expansion is that there is the possibility of a charge fixed point for large values of n. but not more than that. There is no quantitative prediction. So the open problem, which is something which I think is worth investigating, is what is happening for fermions. Because of course we have the QCD transition. The QCD transition has been described within this Pisarski-Wilczek approach, which assumes just the standard Landau Ginsburg-Wilson scenario. But maybe this is not the correct scenario. Maybe that in this case, there is a charge fixed point that controls the finite temperature transition. And here we have no indication for, in favor or against this hypothesis, but I want just to show you that if you take the SU through gauge theory with NF Dirac fermions, and you do the theory in 4 dimensions, instead of 183, you just get 16. So it's a number which is 10 times smaller. So why not in 3 dimension n star f equal to 3? Why not? I mean, since we get a deduction by a factor of 10, I mean, it's really possible that in 3 dimensions, there is a charge fixed point for a value of NF, which is physically interesting. So this is open problem. I have, of course, no answer to that, but this is something that I want, maybe some of you have some ideas how to tackle this problem. Okay, thank you very much.
Okay, thank you, Andrea, for this very nice talk. So we are open for comments, questions, open for discussion. Luigi.
So, Andrea, these models, they all have a Gaussian fixed point as well.
Yes.
And then some other fixed point somewhere else.
This is the stable fixed point. This is where you have a stable gauge fixed point.
Yeah. So how do you know that these results are going to be stable? I mean, the numerical results, not the fixed point, are going to be stable if you add extra operators to the action. In the sense, you could add what would be higher dimensional operators at the Gaussian fixed point that are compatible with the symmetry of the system. But since you have a different fixed point, I mean, you can have naively higher dimensional operators that are actually not irrelevant.
Yes. Okay. Here, what I'm saying is just in the standard framework. I assume that the relevant theory is the renormalizable theory with the same field content and same symmetries. Then I do perturbation theory and I compute the fixed point. This is the basic idea. This is the basis of everything. But this is the basis of the standard exponent expansion approach for any model. So I assume that I'm using exactly the same theory, same field content, same symmetries.
Okay.
I don't know. It's very interesting, but also very hard to build intuition on this. Because to build an intuition.
Speak a little bit louder.
Yeah. It's hard for me, out of ignorance. It's hard to build an intuition because how can you really evade a simple scalar field scenario, the Pisarski-Wilczek scenario when the transition is of second order. So you are really challenging the idea that one can get rid of all the microscopic interactions and only be dominated by symmetries. So how do you have a
no, I didn't understand. In the standard approach, Pisarski-Wilczek, you just forget about the gauge fields. So you're just forgetting about all these microscopic details.
Exactly.
Here I'm saying I want to keep them.
I understand, but the reason why in Pisarski-Wilczek naively we forget about them because we say the correlation length diverges, so who cares about this microscopic interaction?
That's true, but that's the point is. Is that really correct? Because do the gauge fields have no interaction? I mean, because you assume in that theory that only the correlations develop only among the scalar fields, but there is no interaction, long scale interaction, which is mediated by the gauge by the gauge field. Which,
okay, so physically, if the scenario you propose is realized, that would indicate that there are long-range correlations in the gauge
due
sector.
to the gauge fields, yes.
Okay, okay, I understand.
Yes.
Very interesting. Thanks.
Yes, and we know that in some theory, for at least a very large number of flavors, that happens. I know that if this is true, I mean, I don't know exactly what this n star f is in 3 dimensions, but I know that somewhere, if NF is sufficiently large, that happens. I don't know if NF is physically interesting number, but that fixed point exists. Maybe it doesn't go up to, I mean, of course, you can also think that I assuming that there is an analytic continuation up, down to 3 dimensions. So what I see that the epsilon expansion is predictive in 3 dimensions. Of course, there is also that assumption that when I do an epsilon expansion in 4 dimensions, then that predicts me something. I mean, if I'm able to just extrapolate to 3 dimensions, yes, there is also that assumption in these calculations.
Yeah, thanks, Andrea, for the nice talk. I was trying to, a minor point, actually. I was trying to understand your comment that a small kappa, the compact and non-compact model are the same. On the light of the fact, I mean, you know, I'm struggling on the light of the fact that one has monopoles and the other doesn't. You have partly answered this question with when you go to the compact charged field. But I wanted, I mean, you know, I want to understand how this phase transition can be the same, this line can be the same in the absence or in the presence of these objects that are supposed to drive the phase transition itself.
No, the point is that the O3 transition has nothing to do with that. The O3 transition is just related to, is an order-disorder transition driven by the scalar fields. This is the reason why that is not relevant.
Okay, I see. Thank you.
Yeah, thanks. This was very fascinating. I don't know if you followed the session on, when was it, Tuesday? So we just have new lattice results where indeed we are in contradiction to Pisarski and Wilczek, and we see a second order transition for 3 flavors, and in fact more flavors. And we've, of course, no insight into what is the mechanics in your language, but what I was wondering is along the lines of what Luigi was asking. So if you, I think there are new studies already in the making when you add to the Pisarski-Wilczek study higher powers of the order parameter, the picture can also change apparently. Do you have a comment on that or?
Okay, well, in the standard field theory approach, this is the 5-4 theory is a renormalizable theory. So from my point of view, this is a complete theory. I don't need to add anything. Of course, you may think that your description, your effective description is not complete. And then you need to add additional operators. If you add additional operators, you go to something different, which I have no control of course. Yeah, sure. That's correct.
Other comments, questions? Okay, if not, let us thank again Andrea for this very nice talk.